And welcome back to another LeetCode video. Typically I post videos where I try to solve problems and I don't know the answer. I thought I'd try something different where I explain you how to do a problem, how to solve it. And for that we're going to use LeetCode.io, which has this nice roadmap feature that groups 150 curated LeetCode problems into categories. And the categories are the problem or the techniques that you can use to solve the problem. So the linked list problems, tree problems, two-pointer problems, backtracking. And today I thought we'd go into the dynamic programming section, but only the one-dimensional one. There's of course a two-dimensional one, which is a little bit more advanced. But the one-dimensional one is really nice, I think, to get started with dynamic programming. There's some excellent examples that make it really easy to explain how dynamic programming works. And yeah, we're going to look at an easy one to start with, and it's climbing stairs. This is a very well-known one, and you should absolutely know how to solve this one. So the scenario is that you're climbing a staircase, and it takes n steps to reach the top. Now, each time you can either climb 1 or 2 steps. And the question is, in how many distinct ways can you climb to the top? And here are 2 examples that show how to do this, and I thought to explain this, maybe I'll just put this here and make some nice drawings to go along with that. So the scenario is, well, we have a staircase that has 2 steps, right? So we have where we start. Oh, it tries to do, and it has the top. So this is kind of the top where we want to get to, and this is the start. Oh, drawing with a mouse is slow. Okay. Yeah, so, well, how many different ways are there? So I would say this is position 0, this is position 1, this is position 2, and n is 2, right? So this is our input n. Well, we know that we can take 2 steps at once, so why don't we just take 1 step? We're done. So that's one combination to reach the top. What are the other 2 combinations? Well, we can go 1 step to go here, and then we can take another step to reach the top. So in total, we have 2 combinations to get here. And by the way, so there's 1 combination to go here. Now there are 2 combinations to go here. That's why the answer is a 2, right? Now, if we were to extend this and look at the second example, where we have another stair we need to add, then this becomes the top. I'm moving this here, and that would be position 3. So n equals 3. Well, how many different ways are there to reach that position? Well, we know we can go 1 step here, and then we could take 2 steps, well, at once to go here. So that would be 1 way to reach the top. Now the other way to reach the top would be, well, we could first go 1 step, 2 steps, and then 1 step. That's the second way of how we could reach the top, right? But what we could also do is we could take 1 step and 1 step, so from here, and then reach the top. So now we have 3 different ways of how we can reach the top, which are exactly the 3 examples here. And dynamic programming has 2 main properties that you need to have in order to be able to solve the problem with dynamic programming. The first one is that you need to have a problem that you can break down into sub-problems, right? Imagine you have a big problem. Well, you need to be able to break it down into maybe, yeah, I don't know how many, but a couple of sub-problems, smaller ones. And when you're able to solve these smaller ones, right? If you're able to build the overall solution from the solution of the small problems, that is when you have a dynamic programming problem. So the ability to break down the problem into sub-problems and the property that you combine them to a bigger solution, to the overall solution. In dynamic programming speak, this is called overlapping subproblems. So it's not only that you break down the problems into subproblems, but that they overlap, which allows you to combine them later to form the big solution. And here in this example with the stairs, we actually do have that, because if you look closely, you can see that the number of ways to reach the top is the same as the sum of reaching the two previous. So we have two sub-problems: how to reach the first stair, how to reach the second stair, and you can combine them to compute the overall solution to reach the top. And if you were to continue this with the fourth, you would see, that the next is 5 ways. Maybe we should do this really quick, just maybe to sketch it out. Just to show that it's not 1, 2, 3, 4. Let's see, what color are we going to use? Maybe we use green. So obviously we have 3 ways to reach the previous one. That means if we just take one step from here, from each of these 3 ways, we also have 3 ways to reach this new top. But we also have 2 ways to reach the previous one, and we could take a step of size 2 from here, from each of these ways, so which adds another 2. So I hope this kind of illustrates how these small sub-problems can be combined to the overall solution. And and that's pretty much all we need to do when we put this into code. We basically just need an array, and that codes how many different ways are there to reach a specific position. We already know that to reach the first stair, we have 1 way of doing that. We have 2 ways of reaching the second one. We have 3 ways to reach the one at position 3, and we have 5 at that one. Well, what would be the next one? It would be 8, right? And the observer might see that this is a known sequence that we have here, and that is, of course, that's the Fibonacci sequence. And it just continues like this. And you could also think about, okay, what about the edge case when we start? So at position 0, that's, I guess, convention. You could say 0 because we don't have to take any steps. Or you could say it's 1 because we're already there. And if you put 1, it kind of works nicely, so it doesn't break this pattern of adding the previous 2 equals the sum of the third. And this is, I think, also how the Fibonacci sequence is defined. Some people say the first is a 0 and the 1, and then you get the next one automatically. But that doesn't matter. So if we're going to implement a solution for this using dynamic program, this is exactly what we're going to do. We're going to build this array in code. So let's just do that. And how should we do it? Well, we have to define our array of ways. And we have to give it some initial values so that we're able to compute the sum for the next. So we need at least 2 values in our array. Now we have to know what n do we get. So n is at least going to be 1. And at 1, that probably means the first stair. So we could add 1 and 1 to our array. We know that 0 is never going to be asked, but if somebody asks for n equals 2, we know that we have to add them, the previous 2, to get the result. So why not do this? So we're going to say ways equals 1, 1. And now what we do is we iterate until our array has the same length as n. While it's smaller or equal, we're going, than n, we're going to, extend it, our ways array. And we're just going to add the sum of the previous 2 elements. So ways minus 1 plus ways minus at index minus 2. In Python, that gives you the last element. This gives you the element before the last element. And then in the end, you just return ways at index n. That's all we have to do. And we're building out the complete array that way. And let's just check if our indices are right. If n equals 1, then the length of our array is already 2. So we're not going to go into our while loop. And we just return it at index 1. And I think, yes, that's pretty much it. And if n is larger, then, well, if n is 2 or larger, we have to go into the while loop and append it. So let's just run this. That works. And if we oops, wrong button. If we submit this, it should also pass. There you go. We didn't do a runtime complexity analysis yet, but it should be obvious that it's linear in n, because that is how many times we are going to iterate at most, time and space. Now, is there a way of how we can optimize this and reduce the time complexity or the space complexity? Well, if we look at this, we're building up this entire array. We need to go through the entire array, so I don't think we can reduce the time complexity. But what we can do is we don't have to remember all of these numbers. We just have to remember the previous 2 numbers instead of the whole array. If n is 1,000,000, we only need to remember the previous 2 stairs to compute the final one. So to optimize this, what we can do is, let me just this real quick. We just, well, we will still have to create a little seed array in the beginning. Like so. And now what we're going to do is we're going to just keep this area at the size of 2. So, and we can't obviously use the length of ways anymore to determine when we are going to exit our while loop. But what we can do is while n is larger or equal than 2, and then at every step we just reduce our n. So that has the same effect. And now we just need to update what we have in our array. So we will update the array at position at index 0 and of index 1 separately. And we just treat it as a sliding window. So the number at the end moves to the front, and the new number at the end is just the sum of the previous 2 numbers. So ways at position 0 becomes ways as 1, and ways at position 1 becomes the sum of the previous 2 element in ways. So that's all that is needed. And then in the end, just return ways n. And let me just run the test. And just a hint. So if you do something like this, if you write this in one line, the right side is computed before the left side is updated, right? Otherwise, you could think that, okay, ways 1 overrides ways 2, and then we compute the sum. No, that's not how that works. This side is evaluated before that one is updated. So that's why we can do that. Now that the test passed, we can submit it, and we're done. So this is a really nice way of doing this. I think there's also a closed form for the nth Fibonacci number, right? If you use the closed form formula, then it becomes O of 1 time and space. But nobody's going to ask for that in an interview. Yeah. So that concludes our first, I would say, one-dimensional dynamic programming problem. And yeah, and we're going to try to compute the next one in a following video. Thank you.